And let me start sharing the screen. Okay, can you guys see my screen? Okay, all right. So last week we briefly saw what is D2A converters, and we see a lot of problems and issues related to weighted R2R. Then we went to ladder type ADC or steering type ADC. Okay. So now let's take up. Somebody has asked me this problem to solve. I think today we have a lot of problems to solve. Are you guys okay to stay little till 8, 8:30, 8:45? Because we will cover all the A to D, D to A problems. Are you guys okay with that? Let me know in your chat box if you're okay. So that we'll completely see what kind of typical problems they may ask in D to A and A to D converters. Okay, great. Okay, let's start the first problem. Start this problem. First thing what you need to do, consider this as an ideal op amp. So what will happen for an ideal op amp? The input currents and gain is like infinity. So the virtual short concept is applicable, right? And of course there are like infinite bandwidth and all those things. Infinite common mode gain and then infinite differential gain and zero common mode gain. All those stories are there. Anybody got the answer? What is the V naught? Okay, I'll give a hint. Okay, so suppose let's say if you find this voltage, okay, let's say this is some Vx. If you somehow find this voltage, then this according to virtual short, this is zero, and you know this current is equal to this current, right? So Vx minus 0 by 2R, that will be equal to 0 minus V naught by 3R. That's it. Your V naught is just minus Vx by 2. Now the question is how to get that Vx. So you guys heard of superposition theorem? Say yes or no in your chat box. You are aware of superposition theorem? Yes, no? Hey, yes, right. So what superposition theorem says? You know, if there are multiple sources, then first you find the effect of one by disabling the another source. So disabling voltage source means V equal to 0. Disabling current source means I equal to 0. Voltage V equal to 0 means short circuit, right? Disabling current source means open circuit. In this circuit, there are no uh, current sources. There are only voltage sources, right? So what you need to do is we can take up this, right? So what we can do is this. So let me redraw minus plus. This is connected to ground, and here is 2R. This is V0. This is 3R, 2R, right? Then there is 2R. 2R is already connected to ground. This is 2R. Then R, 2R, and I am enabling this source, disabling this one, right? So 2R, R, R2R, R2R, right? This is R2R. This is already at ground. Then this 1.6 volts I am making 0. So this is R. Okay. This is because of superposition, right? I am only considering this source, right? What is this value? 2R, right? This is 2R. Do whatever you want. Somehow find this value Vx. How much is a Vx? If I know that, we know the answer, right? Now to find Vx, you can find the equivalent, right? 2R, 2R in parallel will be R. R, 2R in series, 2R. 2R, 2R in parallel, again R. R, 2R in series, 2R, right? So effectively, if I compute this is 1.6 volt. Then this is, sorry, I forgot what is this value. Okay, anyways, 2R, 2R, R, 2R, then R, then 2R, right? So this 2R is coming in parallel to this, then 1.6, then R, then 2R, and according to virtual short, this is also 0, right? Virtual short, 2R. Now, what is our my aim is to find this value Vx. Where is that Vx? After R, right? Here, Vx. Somehow you need to find this Vx, right? Right. Now, if I combine these two branches, um, this will be, if I combine these two, this will be R, right? This is 2R, 1.6 volt. This is 2R. This is R. This is R. I need to find what is this Vx. Correct. So if I look at this from this point of view, this branch and this branch, they are parallel, right? Correct. So if I equivalently, if I write 1.6 volt, this is 2R. Okay. Okay, something happened. Somebody is trying to join. Okay, fine. This is 1.6. All right. 2R. If I combine these two, like say this is 2R, this branch is also 2R. So it is effectively R. Right. Now you will find the voltage across this node. Right. So what is the voltage across this node? These two are in series, no? So 1.6 volt into R divided by 2R. Are you getting it? So what I found is this 1.6 volt into R divided by 2R. This is what I got. Now from this I can find what is Vx, right? What is this actually? 0.8 volt. So Vx is 0.8 volt into R divided by R plus R, correct? Because these two are in series anyways. Finally, you found this voltage. Now you are finding Vx, right? So this is around 4.4 volt. So you found this as 0.4 volt. What is there in next? Very easy, na? So Vx, the current in this node, current entering the node is current leaving the node because this current is anyway 0. So 0.4 volt minus 0 by 2R is equal to 0 minus V naught by 3R. No, sorry, something wrong I did here. You see this here? Ah, I found this mistake. 1.6 into R divided by, this is R plus 2R, total resistance, right? 3R. Okay. So this voltage is 1.6 volt into R divided by 3R. So the Vx is just divided by 2. That's it. You apply whatever the theorem that you want to apply, whether you want to apply nodal analysis or whatever it is, find somehow what is Vx. So what is this value? 1.6 volt into R divided by 3R. Okay, in denominator 2 is there. This is your Vx minus 0 divided by 2R, that is equal to 0 minus V naught divided by 3R. Okay. So here R gets cancels, R gets cancels. Okay. So 3 gets cancels. V naught is nothing but minus 1.6 volt divided by 4. This is minus 0.4. Right. So V naught because of one node. What is that? 1.6 volt. Right. So because of this, its contribution at the V naught is minus 0.4 volt. Right. Now you find out what is the contribution of this 1.6. Okay. So if you look at this, we have already discussed about this problem, right? So this will be giving minus V reference by 2. This is giving you minus V reference by 4. This node will be giving minus V reference by 8. This node will be giving minus V reference by 16. Correct? So this is nothing is there. So this contribution is 0 at the V naught. Then its contribution is minus 0.4 volt because minus 1.6 volt divided by 4. This is minus 1.6 volt divided by 2 because voltage is not there right now, it is 0. Then this is minus 1.6 volt divided by 8, nothing is there, so 0. Here minus 1.6 volt divided by 16, so minus 0.1 volt, right? So your V naught is nothing but minus 0.4 volt plus minus 0.1 volt. Okay, it's around minus 0.5 volt. Okay, that's what is given. Okay, so Bunty, are you clear with this? Yeah. So my point is, okay, so let me reiterate this. This is 2R, right? This is 3R, 2R, R, 2R, R, 2R, R. This is 2R. This is 2R, let's say. correct? Let's say I'm giving zero point 0.6 everywhere. What is V naught? Could be a question, right? Right? Just focus on this guy. Okay, make everything else zero, zero, zero. What will happen? 2R, 2R, R. This is 2R. This is again R. This is 2R. This is again R. This is again 2R. Right? So what you got is this is 2R. This is 2R. 1.6 volt. This is 2R. Okay. You need to find this voltage. What is Vx? Right? So Vx is very straightforward right now in this case, right? Vx is, now these two are in parallel. So I can make effectively R. So Vx I can write it as 1.6 volt into R divided by R plus 2R. Are you getting it? So what is this voltage? 1.6 volt into R divided by 3R. Right? This is your Vx. Simple. So Vx minus 0. See, this is Vx. This is 0. The input current at this node A is Vx minus 0 by 2R is equal to 0 minus V naught by 3R. So what is Vx? 1.6 volt into R divided by 3R by 2R, that is equal to minus V naught by 3R. You see this? What you got? V naught is minus 0.8. Means if I take 1.6 as V reference, what is V naught is giving? Minus V reference by 2 here. If it is 1 point. Obviously, if you try this, we already got minus V reference by 4. Why minus? Because it is an inverting amplifier, right? Now this is will give you minus V reference by 8. This will give you minus V reference by 60. That's what I am trying to iterate. Okay, there is no other thing that. Okay, how many of you are clear? Are you guys clear with this? Somehow you try to get Vx. That's it. If you know Vx, you can apply that and then you can get it. Okay. Hey guys, this is not a YouTube video. Okay. This is a live session. Can you type yes or no in your chat box? Did you guys understand this? Yes. Okay, fine. Now, what about this one? This part is little mathematically involved. Like there is a huge network here. So start from here, you have to come here till this point. Otherwise, everything else is same, right? Okay, right? Now try this problem. A 4-bit, this is D2A converter, is connected to a free running 3-bit up counter as shown in the figure. Which of the following waveforms will be observed at V0? This is 4-bit D2A converter and this is up counter, 3-bit up counter. Try this. Okay, Which option could be best? Okay. Any answers? Okay. So let's take some reference. Okay. We already heard of V resolution, right? If the input changes by one LSB, the output changes by one time V resolution, right? So this is the first state, 0, 0, 0, right? Then they are saying it is a up counter, free running 3-bit up counter. So 0, 0, 0 means assume that V naught is 0. Then what will happen? Q naught will become 1, right? So 0, 0, 1. So what will happen? There is a 1 LSB increment. So let's say V resolution. Then what will happen? You will get 0, 0, 1 is over 0, 1, 0. Okay. So 0, 0, 1, 0. How many increases? 1 LSB. So the output increases by 1 resolution. So it will be 2 times V resolution, right? 1 V resolution increment. That's it. Next, 0, 1, 1. Right? 0, 1, 1. So what will happen? Again, this is 1 LSB change. So what will happen? You will get 1 resolution output increase. Now what is happening? Your Q2 is 1, but Q2 is connected to D3. So 1, 0, 0. What is this actually? If you look at it, this is 1 time V resolution, 2 times, 3 times. This could be 8 times V resolution, right? Then 1, 0, 1. This is 9 times V resolution. Then 1, 1, 0. This is 10 times V resolution. Then 1, 0, 1, 1. This is what? How many times? 11 times V resolution. After that, what happens? Again, you will get 0, 0, 0, 0. This is again 0 you will get. Yes, correct. Now, if I plot it, let's assume that V resolution is 1 volt. Okay, if I am plotting it. Hmm. So, this is with respect to time. This is voltage V naught. Um, so, if I plot it, initially 0, then 1 volt, then 2 volt, then 3 volt, right? This increment is 1 volt. Na? So, from 3, it is going to 8. It will go up like this because now the change is 5 volt. Then what happens? Again, from 8, it will go to 9. The increment is not that great. Then 10, then 11. Then again falls back suddenly, like this, 0. From 11, it will become 0. Then again, same cycle will repeat. Again goes up, goes up, goes up, goes up. Again come back. Are you getting it? If you look at C, it is incrementing stepwise, but that is not the case, right? So this is not a right answer. And what is it showing? Increasing, then decreasing. Oh, there is no concept of like that, right? Now here it is increasing, then going up, then again increasing, again going, coming down slowly. No, it is falling straight, right? So option B could be the right answer. Okay, are you guys clear with this? Say yes or no in the chat box. Okay, you have any questions to ask me so far? Okay, Patsarathi, you are saying yes. Okay, okay, fine. Sorry. Okay, great. Thank you. So, then you solve this problem. This is also called as steering DAC or inverted R2R. And you guys are very lucky because this gave for 4 mark. Very easy. Right? Any answers? 0.125. Okay. So somebody is saying option C. See, this is called as what? Current steering DAC. The reason is this. Okay. This one is very interesting thing. You look at this, right? If you take this op amp as ideal, correct? Then there is a virtual short concept applicable, right? Then this is 0 volt. So you look at this is a physical ground, right? And this is a virtual ground. So either you connect the resistor to physical ground or connect to the virtual ground. So if you connect to the virtual ground, you are pumping the current towards this node. Okay, you're pumping the current, and this current sums up, and then the other current will come here. And since this input current is zero, whatever is the current that is coming in has to flow to the output node. Okay, this is very wonderful actually if you look at it, right? So if you look at that, this is minus plus, this is ground here, right? And you have VR, and there is 2R, R, 2R, R, 2R, R, 2R, and there is a 2R resistance here, right? You have two nodes. Now you have a choice, like these are the bits. Such a simple network. You see this? This is okay. B3, B2, B1, B0. So if B0 is 1, then you connect it to the output side and you steer the current to the output. If B0 is 0, then you steer the current to the ground. So no current is going out because of this resistor R, right? So that's why it is called current steering. And at any given point of time, these currents will remain always same. There is no change in the current. Why? Because this, you look at this node, right? Right, control L. Where is it? Yeah. You look at this other end, either it is connected to the virtual ground or connected to the physical ground. So the potential always remains same at this end. And this end potential will remain same because VR will remain same. Are you getting it? So at any given point of time, this is the beauty of this. At any given point of time, at any given point of time, right? Whatever may be the value of B3, B2, B1, B0, the current across all resistors remains same. Because of this, there will be a predictable error that we can achieve. Because of this, linearity can be established. But if you look at the other way around, okay, if you look at this circuit, R2R ladder, okay, if there is one more voltage source here, then the current changes here, current changes here, current changes here, everywhere current changes. If there one more, so for different combinations, the current across the resistors are different. But for this, no matter whatever the combination is, B3, B2, B1, B0, the other end, either it is at a physical ground or a virtual ground. So the current remains always same. So the non-linearity can be predicted. Okay, that's why it is superly used in the circuits. All right. I want to emphasize this how good it is. All right. Now let's go back to the problem. Right. So if you look at this problem, right, this is 2R, this is ground, this is R, this is also at ground, this is R, this is also at ground potential, right? This is R, this is also at ground, then there is 2R here. Okay, because I want to find what is the current that is going through. Now, what is the effective resistance seen by this VR? What is effective resistance? R 2, this is 2R, 2R, R in series 2R, 2R, 2R parallel R, these two are in series 2R, these two are in parallel R, these two are in series 2R. So, this is VR, this is 2R, this is also 2R. So, effectively what VR sees, the impedance is R. So, what is the current drawn from this? IR is equal to just VR by R. This is, let's say, IR, that is equal to VR by R. Right now, not only that, if you observe this, right, if I look at till this point, if I look at till this network, you see 2R, 2R, R, 2R, R, 2R, R, correct? So there is a current that is coming like this. There is 2R here, ground, and this is R, this is also R. Okay. Now IR sees equal resistance here, right? It is also 2R, this is also 2R. This will become IR by 2. This will be IR by 2 because current equally divides, right? So if I remove the erase all the ink. So if this is IR, that is equal to VR by R, this is going to be IR by 2. This is going to be IR by 2. If we do the same iteration, this is going to be IR by 4. This is going to be IR by 4 because IR by 2 divides here equally because this also sees 2R here, this also sees 2R. So here this is IR by 8, here IR by 8, this is IR by 16, this is IR by 16. See whatever the IR by 8 that comes here, right, sees 2R, 2R parallel. So obviously current will divide, right? IR by 16. Now the question is what is I? For that I is IR by 16, right? So what is IR now? IR is nothing but just VR by R, right? This initial voltage, initial current is VR by R. So VR is 10 volt, R is 10 kilo ohm, right? So 10 gets cancelled. This is 1 milliampere, right? So I is 1 milliampere divided by 16. This is around 1000 microampere divided by 16. Uh, how much is this? Is it 62.5? Am I clear, guys? Yeah. So you need to find what is the total. Okay, fine. I will do this here, right? This is 2R. This is R. This is 2R. This is R. This is 2R. This is R. This is 2R. And this is what is given, right? This is VR. Now I want to know what is the total current drawn. from this to find out what is I here. Correct? Yes or no? Who is that asked the question? Right. Now for that to find what is IR, you need to find what is this total resistance seen by VR. For that I am calculating the effective impedance. So if you calculate effective impedance, this is 2R to R parallel R, then 2R, then R, then 2R, then R, then 2R, then 2R to R parallel R. So effective impedance seen by VR is just R. So what is this current? Yes. Yes, exactly. No. See, if you look at in terms of potential, right, it is zero only, no? So how does it make any difference? Whether it is at physical ground or a virtual ground, right? So the total current drawn from VR is IR. Let's say, what is that IR? VR by R. Now this IR gets divided like this. This is IR by 2, IR by 2. Why? Because this network is also 2R only, entire thing. Then again, this is IR by 4, IR by 4. Then you know the story, right? Same thing. Current equally gets divided. Okay, guys, is this clear? Say yes or no through your chat box, please. Uh, Gopinath, could you please cross-check your answer? Where it went wrong? Right. So the next question is this. What is V naught now? Now you look at this. IR by 4 is coming. Very simple. This IR by 16 is coming. So what is the total current? Let's say this is I. And this flows like this. And this is 0. I can write V naught equal to minus I into R. Yes. So V naught is minus IR by 4. IR by 4 current is directed towards output plus, I mean, minus, let me not complicate this. Okay, this is very such a easy problem. Okay, so this is IR by 4. So what is I? IR by 4 plus IR by 16. So what is IR? VR by R. Let's put it like that. So I is VR by 4R plus VR by 16R. So V naught is the total I into R. Okay. So what is this? Minus VR is 10, right? VR is 10 volt. 10 by 4 plus 10 by 16. This is 5 by 2 plus 5 by 8. So what is this? Uh, this is 2.5. What is 8 by 5? 8. 8, 5. 48, 20, 16, 5. Right? 0.625. So 2.5, 0.6255 to 11, 3. Right? Minus 3.125. Huh? That's the right answer. Are you guys clear with this? Wow, good man. Today you people are very active. Good. Nice. Okay. So these are the typical problems that one can expect. Okay. More than this, I don't think so. Anything else is there? And I got some more problems. Today, unfortunately, I was busy with my experiments. I could not able to write it. Now I'm writing. So the step size, you also call it as delta R resolution, is 10.3 millivolt for a DAC. Right? So 0.0000000 input is applied. How many inputs? Zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the input. The output is 0 volt. Right. So what is V naught if D in is 10110111? Okay, in volts. Step size, remember guys, step size is also called as a resolution. Resolution is 10.3 millivolt, and for D in 9 zeros, output is 0 volt. What is D V naught if D in is 1011 01111? It looks very difficult, but it's not that. Let me see if there are any other problems with you guys. A lot of problems on ADC. Any answers? Hey guys, what happened? You got scared of the number or what? Okay, now I ask somebody to do it on behalf of me. Okay, who will I do? Who will I- Okay, Ramesh, would you volunteer to solve this problem? Okay, leave it. I'll do that. Let's understand what is that. Uh, you know, Forget about this thing, whatever they gave. 3.75. Let's see. Let's take 3-bit DAC. Hmm? 000 output is 0. 001. What is this? One LSB change results in 1 VRES. Correct? 010. What is this? 1 LSB increment result in this. 011. 3 times this. 100. 4 times this. 101. 5 times this. 110. 6 times this. 111. 7 times this. Now you look at this. Whatever is a binary number here, you are getting a decimal equivalent, right? 111, you are getting 7. So what is the decimal equivalent of this? 1011011111. This is 2 power 0 plus 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6, 2 power 7, 2 power 8. 2 power 8 is 128, 64, 32, 8, 4, 2, 1. This is 15. So 128, 64, 32, 15. Mm-hmm. Ah, yeah. Oh my God. Remaining people are sleeping, huh? Remaining are correct, no? Okay, fine. 256, 64, 32, 15. 6 plus 4, 10. 10 plus 17, 11, 14, 16. 367. 367 into V resolution, right? 367 into 10.3 millivolt. How much is this, boss? I'll open my calculator. Calculator. 367 into 10.3. Oh, 3780.1. 3780.1 millivolts, approximately 3.78 volt. This is 3.7801 volt. Okay, someone else got some other answer actually. 3.75. Okay. Ramesh, why it is 3.67? Did I do something? Oh, not my mistake, right? Okay, Kushbu, how come you got 3.7? Ah, okay, fine. Done. So let's move on. This is one of the problem I wanted to solve. These are basic problems I wanted to solve. Okay, let's move on to this DAC. That's it. Nothing else we can discuss much on. ADC. Hmm? You have analog input. You need to get digital output. That's it. So first concept. Okay. Don't ask me how it works and all those things. Right? Like this is an AND gate. This is VA. This is just comparator. Then there is an AND gate. And there is a clock source. And this is a counter. Now let's say for sake of understanding, I'll take 4-bit counter. 4-bit up counter on that. Okay. So Q3, Q2, Q1, Q0. And this is enabled by a clock. Alright. The output of the clock is given from the AND gate. Now you have outputs right here. Now you have something called DAC. That is the reason why we discussed DAC first. Okay, and every DAC comes with some V resolution. For our understanding, let's take V resolution as one. Means for every in one increment at the counter side, the output of the DAC, Okay, this is VDAC. That's it. Now, how does this work? Very simple. Let's take VA as 6.2 volt. Okay. Now, initially, the counter will be 0. So, the output is going to be 0. So, VDAC is 0. 6.2 greater than 0, right? So, output is 1. So, the clock will be supplied. What will happen when you supply the clock? It will become 1, right? Now, V resolution, we have already seen. Whatever is this, multiply with the V resolution. You will get the output. Now, you got 1. So, 6.2 greater than 1? Yes. Again, you get 1. Again, this is supplied. So, what will happen? The counter increments by 1. 1, 0. Then what happens? Okay. First 0, then 1. Now it becomes 2. Then 2 will be supplied. 6.2 greater than 2? Yes. So output is 1. Clock will be supplied. Then this is 1. Then output will become 3. 3 will be here. 6.2 greater than 3? Yes. Then clock will be supplied. Then the output will, counter state will change to 0, 1, 0, 0. Now output will become 4. 4 will be supplied here. 6.2 greater than 4. The output will be 1. Clock will be supplied. Here it will become 0, 1, 0, 1. Then output will be 5. 5 will come here. 6.2 greater than 5. Yes. Then again clock will be supplied. So the counter increments because it's up counter, no? Now 0, 1, 1, 0. Output will be 6. 6 will be here. Still the output is 1. Clock will be supplied. Right. Now what happens? Output becomes 7. 7 will be supplied. 6.2 is less than 7 ohm. That is the first time, the output generates 0. 0 means here also 0. 0 means nothing will happen. This will be as it is. So your digital output is 0, 1, 1, 1. Right? So for 6.2 volt, your output is 0, triple 1. Okay. All of you understood this? So simple, na? Say yes or no to your chat box. Right. So here the issue is uh, the conversion time, for example, the maximum or worst case conversion time. Right. So here, since it is 6.2, it took 0, triple 1. Let's say, uh, assume that this delay is 0, this delay is also 0, okay, and this delay is also 0. Assume that. What happens is you have to wait for this clock, right, between one to another, correct? So suppose instead of 6.2, if I have 15, then this should go till 1, 1, 1, 1. Are you getting it? So it took almost 7 cycles to come to this point. It may take 15 cycles, right? 15 into clock frequency or clock time period. Since it is 4 bit, if it is n bit, 15 means 2 power 4 minus 1. N bit means 2 power n minus 1 into t clock. Are you getting it? So it is in the order of 2 power n. If the number of bits are more, then the delay is more. Are you getting it? And also, you look at this comparator, right? Correct. So let's say, for example, if I take this value as 6.03 volt, and here this is 6 volt. If it is ideal comparator, then output will be 1. If it is non-ideal, depending on the characteristics of the comparator, output may become 0 also. That means indirectly your counter output is decided by how good the comparator is going to be and how well the DAC's conversion is doing. Forget about DAC, it's not a big issue, but comparator, how good it is going to compare these two values. That means the output is decided by the circuit elements, right? So for counter type ADC, maximum conversion time is in the order of 2 power n times t clock. Okay, minus 1, I'm just thinking. Then accuracy, how good? It depends on circuit elements. And circuit elements uh, performance depends on many factors like temperature, okay, and various other issues that are involved in biasing and all those things. So that's how it is. So we cannot trust it reliably, and it's not fast also. It's very small, very slow. If you take n equal to 10, then it is 2 power 10. So it's up counter, right? It will start from 0 0 0 0 0 0, then it will move on. Correct? Maximum conversion time is very high. All right. So there is some other uh, ADC. The second type that I will discuss is SAR type ADC. What is this? Successive approximation type. Correct? How it works is very simple. Okay. Same story, plus minus. There is a clock. Okay. And there is AND gate, right? And it's not a clock source. It is just one here. Okay. And here, this is SAR register. Okay. Successive approximation register. It is a bit different from counter. Everything else is same. Okay. This is your DAC and you have V resolution and the output is coming here as VDAC output, and this is VA, again 6.2 volt. Okay, now this only thing different is instead of up counter you have SAR. So how does that work is simple. What is up counter is doing 0 0 0 0, then 0 0 0 1, 0 0 1 0, 0 0 1 1, and so on. It's doing like this, right? This is basic up counter. All right. Now what SAR does is this. Something special about SAR is it doesn't start with 0 0 0 0. It will start with 1 0 0 0 instead of MSB. It makes it 1. So next step is here there is an input, right, to this input. Okay. If that, let's say that is called as E naught. Hmm? If E naught is 1, what happens is it will keep this one as it is, right? It will make the next MSB. What is the next MSB here? Here, this one, right? It will make this as 1, right? And remaining, it doesn't change much. This is how the working principle of SAR is. Suppose if E naught is 0, what happens is this will make 1, the MSB to be 0, make the next MSB 1, same thing, 0, 0. That's it. So what does it mean? E naught 1 suggests that whatever the VA is more than what the counter is showing. So don't change the MSB, change the next MSB to 1. That's what it indicates. Correct? No? If E naught is 0, that means that whatever the VA is, right, less than whatever is showing. So make your MSB 0, make the next MSB 1. That's it. If E naught is 1, keep it as it is, change the next MSB to 1. If E naught is 0, change the MSB and go to next MSB and start performing the same thing. Correct? So you are done with this, the first MSB. Now let's talk about second MSB. Okay, and go on. Right? If E naught is 1, two possibilities. E naught is 0. If E naught is 1, don't change that MSB also. This, I mean, of course, forget about the extreme MSB. 1, 1. You move to next MSB, right? 0. I'm just trying to decorate it. That's it. If E naught is 0, that means that now this thing is over. 1 will be like that. This you make it 0 here, right? Go to next MSB. That's it. The principle is same. If you receive E naught as 1, don't do anything to the MSB. Change the next MSB and keep doing the iteration. If you receive E naught equal to 0, change the MSB to 0 and change the next MSB. That's it. Okay. Now how does this work now? For ease of understanding, what I'll do is I will consider the same 6.2 volt and the initial, sorry, this is 1,000, that is initial state of this SAR. Then this is Q3, Q2, Q1, Q0. I am assuming that V resolution is also 1, right? Now what is initial state? Initial state is 1,000. Let's see what will happen to the next state. Now this is 1,000. Based on our understanding, this output is going to be 8 volt, correct? This 8 comes here. 6.2 volts is less than 8 volts. So the output is going to be 0. Then here it is going to be 0. Then it is asking it to reset this to 0 and make the next MSB 1. This is the next state. 0, 1, 0, 0. Now let's see what will happen to the next state. Okay, let me pick up this blue pen. Now 0, 1, 0 means it is 4. So the 4 comes here. 6.2 is greater than 4, right? That means when this is 1. So now this is already over in the previous cycle. Now 1 has come. That means that don't do anything to this, change the next one. Right? Keep that one as it is. Are you getting it? So you got 0, double, 1, 0. Let's see what is the next state. Now 0, double, 1, 0 is 6, right? 6 old. So 6 will come here. 6.2 greater than 6, correct? So it is 1. 1 means the output is here 1. E naught is 1. That means don't do anything to this. Change this to 1. 0, 1, 1, 1. Now what will happen? 0, 1, 1, 1 is 7, right? 7. So 6.1, 6.2 is less than 7. So 0 will come. 0 will be there. Output will be 0. Since it is received 0, you have to make this to 0. After this, nothing else is there. So again, back to this. So if you look at it, what you are doing is you are not incrementing in terms of one LSB at a time, like up counter, right? What up counter is doing? Incrementing one at a time and then comparing every time. Here it is not doing like that. It is comparing bit by bit. You see, bit by bit it is doing. Correct? How many iterations it took? This is the first iteration, second iteration, third iteration, fourth iteration. By fourth iteration, you have the answer. Now, it is not only true with 6.2, even if you take 15 nodes, the same thing is happening. Right? So, I took 4-bit DAC and I got it in 4 iterations. I can say 4 clock cycles. If I take n-bit ADC, sorry, this is not DAC, this is ADC, I will get it in n times clock cycle. Now, relatively faster compared to counter type. Are you getting it? Here, the complexity is involved in design of SAR, and also again, it depends on circuit elements like comparator and how accurate the comparator is, how good the comparator is will decide, the performance of this SAR type ADC. Are you guys clear? Yes or no? There was some problem actually for this. Sure. Where is it? Okay. Anyways, if the problem is not there, who cares right now? Okay, you do this problem. Okay. Find out the series of states the SAR traverses before it gets stabilized. Okay. VA is 11.6 volt. This is one. This is SAR. Q3, Q2, Q1, Q0. 4-bit DAC. And V resolution is 1 volt. Okay. So find out the series of states that SAR traverses before it gets stabilized. So for any conversion, the starting state is 1,000. Then you have to figure out what is the next state. Okay, the first state. Answer, please. What is the first state? 1000. After that, next state. 1100. Okay. So 1000 first. So the output is going to be 8 volt. This is 8 volt. 11.6 is greater than 8. So output is 1. Correct? Yeah. Good, 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 guys. Keep doing, keep doing. This is 1. Since it is 1, don't do anything. Don't change anything. Change this, right? Now you make this to 1100. So 1100. Then what will happen? 1100 is 12, right? Now 12 will be there. Now 12 will be there. 11.6 is less than 12, right? The output is 0. Because of this, output is 0 here. 0 means you change this to 0, change this to 1. The next state is 1010, right? Correct? So 1010 is 10, right? This is 10. This is output is 1. This is 1. So keep this 1 as it is. Change this to 1. So the next state is 1011. So what is 1011? 1011 is 11, right? 11. 11.6 is greater than 11. That means 1. The output is going to be 1. That means that don't do anything. Change the same thing. Nothing is there. So 1011 will be stabilized. That's it. These are different states that are traversed during the stabilization process. Are you guys clear with this? Right. So as I said, SAR type ADC, here maximum conversion time is n times t clock. And again, the performance depends on circuit elements. And the best part about this SAR type is this. Whether you take 6.2 or you take 11.6, how many iterations it took? First, two, three, four. Same thing, right? Here also 1, 2, 3, 4. Right? So this is called uniform conversion time across all the inputs. Doesn't matter whichever the input you give, it's uniform conversion time, right? So we saw this one, the speed of the maximum conversion time is 2 power n clock, and this is around n times t clock. So how to reduce this speed, or how to reduce the delay conversion time? So you have something called as flash type ADC. Are you getting it? So for a flash type ADC, I think you might have seen in many books. Okay. So I can just take 2-bit ADC, right? So let's say R, 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 and we have priority encoder 3, 2, 1, 0. Correct. This is highest priority. This is lowest priority. So the output is B2, sorry, B1, B0. Are you getting it? So what's happening is this. You take a comparator, plus minus, this is V in. You compare with some reference voltage. Okay. So what is this voltage? Let's say this is VR. Correct. Now all these four resistors are in series, even though this current is zero anyways. So this voltage is nothing but 3 times VR by 4. What about this voltage? VR by 2. This is VR by 4. Now you take one more comparator, plus minus, give V in to one terminal, compare with another terminal, right? You already have reference voltages to compare, right? Now, if all these are zero, for example, that means that definitely whatever is the leftover will be greater than zero, right? By the way, these are all unipolar ADCs, whatever we're discussing. Unipolar ADCs, that means only positive supplies, positive input voltages, right? Now, for example, if I take Vin equal to 1 volt, VR equal to 4 volt. So this is equal to, come on. Now this is 3 volt, this is 2 volt, this is 1 volt, right? Now Vin is 1 volt, this is 1 volt, this is 1 volt, this is 1. Okay. So let's say 1.1 volt, not to have any ambiguity. Okay, 1.1, 1.1, 1.1. Okay. Now 1.1 is less than 3, so this will be 0. This 1.1 is again less than 2, this is 0. 1.1 is greater than 1, so this is 1. This is anyways become 1. Since this priority encoder, 3 is highest priority, 0 is lowest priority, 1 is better than 0, so this is 1. Whatever is decimal equivalent of, binary equivalent of 1 will be coded here. B1, B0. What is binary equivalent of 1? 0, 1. So for your 1.1 volt, your output is 0, 1. And if you look at it, how much time does it take? Okay. See, there is already network here. RRRR is already generated and kept it ready. As soon as you apply V in, the output will be ready because it's all combination delay of comparator and delay of priority encoder. If I assume the comparator delay and priority encoder delay is very negligible, so it will ideally take 0 seconds. That means flash. Within no time, you get B1 and B0, no matter whatever the V in that you apply. That's why it is called flash type. And also you are using comparators, like lot of comparators. Comparator type ADC, and you have priority encoder, correct? So for a 2-bit ADC, what is the encoder that you have? 4 by 2. How many comparators that we have? 3 comparators. By now we are very clear, right? Why the fourth comparator is not required. It's useless. What it is not if it is not greater than any of these, obviously this will be greater than 0. Obviously B, right? If it is non-zero, right? Comparators are 3. Are you getting it? So if I take 4, I mean, if I, because I took 2 bit, that means 2 power 2 minus 1 is equal to 4. If I take n bit, the comparators will be 2 power n minus 1. Now you can imagine if it is a 3-bit ADC, you will need 7 comparators and 8 resistors. If it is 4-bit, 16, then I mean comparators are 15. If it is 5-bit, 6-bit, 7-bit, 8-bit, after one point of time, the hardware becomes so bulky. If you take 10-bit, for example, you want to build a 10-bit flash type ADC, right? Your priority encoder should be 10 power 10 by 10. Then comparators would be 10 power 10 minus 1. This is 1023. So huge, bulky. Okay. So if you want, if the application is faster, for example, where can you use this kind of thing, right? Suppose you are owning a iron ore, okay, and you want to transport the iron ore, and you are okay with there are some errors, half kg, 10 kg, or 5 kg change in the iron. It's okay, fine. You can use this kind of converters. For example, you are like a KGF guy. Okay, you have gold, and can you afford loss of 1 kg? You saw the movie, right? He cannot afford loss of 50 gram or 100 gram also, right? So that's a different story. Okay, he goes for that something different. But my point is, if my question is, if are you okay to afford, if you are a gold shop owner, goldsmith or somebody, are you okay to make your customer wait for 5 minutes, or you are okay to lose 10 gram of gold? Losing 10 gram of gold is most of the people get heart attack, right? So you're okay with, for the customer to wait for 5 minutes or 10 minutes, whatever it is. So depending on the application that you're using, okay, right, the end application, okay, and make sure that you can use whatever the uh, ADC that suits your application. Are you guys clear? Are you guys can you guys hear me? Are you guys there or no? Uh-huh. All right. So based on this, there are few questions. Okay. So in a comparator type ADC, number of comparators required for 3-bit ADC is dash. Okay, 3, 4, 7, 8, none. Hmm. 7, right? Okay, the question is this. A 12-bit ADC is operating with a 1 microsecond clock time period. Hmm? And conversion time, please pardon me for my handwriting. I am super good with my handwriting. Okay. Even I can't read for myself after writing. Okay. So that good it is. And that's why I'm reading. I'm reading it again. 1 microsecond clock period and conversion time is seem to be 14 microsecond. So the ADC must be, what do you think is the ADC? 12-bit ADC is operating with a 1 microsecond clock period and conversion time is seem to be 14 microseconds. So the ADC must be of dash. I'll write meanwhile one more question. Okay. V resolution of a ADC is zero point 0.5 volt. Okay. So this is a counter type ADC for an input of 6.6 volt. The digital output of the ADC will be dash 1011 1101 1100 1110. Okay. Okay, what's the answer for this? The previous one? 12-bit ADC is operating with a 1 microsecond clock period and conversion time is seen to be 40 microsecond. The ADC must be of dash. Okay, right now I know people are thinking about it. Forget about integrating type. This is not there, let's say. Answer is exactly. Why? Because you see, they didn't tell conversion time for a particular digital input. It is said just seems to be 14. That means that they are saying it is uniform. They are mentioning it's uniform conversion time. It's not particular to any input. Are you getting it? So directly, blindly, you can say this is AI type. For flash type, what happens? Zero. For counter type, it will be 2 power 12 into 1 microsecond. For integrating 2 into 2 power 12 into 1 microsecond, that we will see later. Okay, let's discuss. Let's not discuss about right now. Okay, are you guys clear? Okay, all right. This is the last problem of the day. I am also too exhausted. After this, we will see in the next session. Next session also, if you are interested, we will take 2 hours. That will be like the last session on this digital. You can come up with your own problems and ask me whatever you want. So what is the counter here? Like ADC, it is counter type ADC. Hmm. 0, 0, 0, 0, 0, 1, then 0, 0, 0, 1. This is zero point 0.5. That's what it is saying, right? Resolution. This is 1. This is 1. I mean, clock is applied. 0, 0, 1, 0. 1 volt. 6.6 is greater than 1. This is 1. Clock is applied. Then 0, 0, 1, 1. 1.5 volt. Clock is applied. 0, 1, double 0. 2 volt. 0, 1, 0, 1. 2.5 volt. 0, 1, 1, 0. 3 volt. 0, 1, 1, 1. 3.5 volt. 1 triple 0. 4 volt. 1001. 4.5 volt. 1010. 5 volt. 1011. 5.5 volt. 1100. 6 volt. 1101. 6.5 volt. 6.6 is greater than 6. Okay. So what will happen? 1110. 7 volt. Now it will become 0. No increment will take place. The answer is triple 10. Are you guys clear with this? Any questions? Ask me. Otherwise, we can leave. I'm packing my bag. Okay, guys. Did I make you guys feel digital easy or difficult? Yeah. Literally, you no need to prepare for digital. Just you need to directly go to the exam and then write. That's my intention. Okay. Great. Thank you, guys. The next session will be 2 hour session. Let me know whatever the questions that you shoot up. No problem. Thank you. Bye.